All right, welcome everyone. For those of you who don't know me, my name is Jillian LeClaire and I'm your Director of Alumni Engagement here at Florida Tech. And I want to thank you all for joining us for today's Lunch and Learn lecture. I'm excited to partner with Florida Tech faculty members, Dr. Kelly Hunsucker and Dr. Austin Fox, to provide this lecture for you on the restoration of the Indian River Lagoon. The lecture will be about 45 minutes with 15 minutes at the end designated for question and answers. That said, if you think of any questions throughout the presentation that you are worried you're going to forget, feel free to type them in the chat box whenever, and they can circle back and answer them at the end of the presentation. Lastly, please kindly leave your microphones on mute throughout the duration of the lecture to prevent any audio feedback. And to get a better idea of who is joining us today, I am going to launch a quick poll with 4 questions. Give us an idea where you're coming from, what your relationship is to Florida Tech and the Lagoon. So go ahead and take a minute to do that. This is exciting. I get to see all the bars fill in as you guys are submitting. All right, I've got 70% submitted. Just give you another few seconds. All right, 3, 2, 1. I'm going to end the polling now. All right, so when did you attend Florida Tech? We have the highest representation with 30% from the 1970s, and then the second highest with 27% in the 1980s. I'll share these results with you guys so you can see. So a great representation throughout the decades. And then we have some folks who are just members of the community who want to learn more about helping lagoon health. So that's great. Thank you for joining us. What areas did you get your degrees in at Florida Tech? The majority science, which is very fitting for this topic, with 54%, 24% engineering, and a few from the other colleges. Where do you currently live? We have 40% joining us who are residents in the local area who are neighboring the Indian River Lagoon, 46% on the East Coast, some from Central US, a few from West Coast. And for those who are joining us who are international, if you want to type in the chat box where you're located, that would be fun to see. I saw on the registration list, we had 2 people register from Belgium, so maybe that's you guys. And then, have you attended a Lunch and Learn lecture before? 60% said this is my first one, so welcome. I hope you enjoy it. And then 40% said that yes, they've been to a couple. All right, so stop that. And I will get into introducing our presenters today. So Dr. Kelly Hunsucker is an assistant professor of oceanography at Florida Tech in Melbourne, Florida. Her research focuses on benthic organisms, such as algae, barnacles, oysters, mussels, and their settlement on man-made structures, an occurrence known as biofouling, which she'll talk about. She is funded by the Office of Naval Research to study marine paints and novel systems, such as ultraviolet light, to determine their efficacy in preventing biofouling. Dr. Hunsucker's other projects involve ecologically engineering solutions for improved water quality and estuarine waters. She is currently investigating alternatives to plastic for the increased growth of oysters in the Indian River Lagoon. In addition to teaching and research, she is heavily involved in Indian River Lagoon-based outreach programs and marine science summer programs for children at Florida Tech. And additionally, just yesterday, she was announced the winner of the 2021 Dr. Mary Helen McKay STEM Award from We Venture, which is Florida Tech's Women's Business Center, for her work to help create and foster the next generation of STEM professionals, including partnering with the Florida Department of Education to provide support for minority at-risk and underprivileged students for cost-free camp attendance for exposure to STEM fields. So congratulations, Kelly, for that award. Dr. Austin Fox is an assistant professor of marine sciences and oceanography at Florida Tech, also in Melbourne, Florida. His research focuses on biogeochemical cycling of trace metals and nutrients in the water and sediment of coastal systems. Nutrients are studied at Florida Tech to investigate eutrophication, one of the leading environmental issues in coastal oceans around the globe. Excess nutrients contribute to algal blooms and reduced water quality that can lead to losses of seagrass, reduced biodiversity, hypoxia, and fish kills. Dr. Fox's research investigates the sources, sinks, cycling, and speciation of nutrients in coastal systems. He is also studying inputs of nutrients and muck components through creeks and rivers and the efficacy of muck remediation efforts, including dredging, capping, aeration, and the use of innovative water treatment technologies. And with that, I will turn it over to our experts.
All right, thank you. So I'm gonna get things started. Hopefully, there we go. Okay, so everyone should be able to see my screen now. Is that correct? I'm just checking. All right, thank you. So thank you for the introduction. So Austin and I are going to tag team this presentation, and we're going to talk a little bit about the Indian River Lagoon Research Institute, some current issues with the lagoon, and then talk about how we are trying to tackle and improve the lagoon. So some of our own kind of specific research here at Florida Tech. The Indian River Lagoon Research Institute started really after the 2011 algal blooms that we saw in the Northern Lagoon. And as scientists, engineers, educators, we wanted to be able to do something, and we realized we all had this collective knowledge, but maybe weren't necessarily using that knowledge and working together to tackle some of these problems. And so that's kind of how the Research Institute started. We have quite a few faculty and staff members working, I think over 20, all in very diverse fields, engineers, scientists, mathematicians, those that are more into the policy and management. So it's really nice. We really have a wealth of information. But there's a lot of current problems with the Indian River Lagoon. And so Austin and I put together just kind of a quick overview of some of the issues that our lagoon is facing. And so some of the big ones are overfishing and habitat loss. Something that I didn't realize that used to be prevalent in the IRL are these beautiful sawfish, which were almost hunted to extinction because of the rostrum that people wanted to hang as a trophy on their wall. But more importantly, and I think something that's really hurting us, especially ecologically, are the oysters and clams, which were harvested quite extensively in the 80s and the 90s, and we're still struggling to bring back some of these populations. And the oysters and the clams are so important because they're filter feeders, and they remove a lot of the algal and other turbidity from the water column. So not kind of having these liver and kidneys, so to speak, of the lagoon has led to some of the issues that we're seeing currently. Some other issues we have are with muck, and this is where Austin, Dr. Fox, is more of an expert than me, but he's agreed to let me talk about this slide, so hopefully I do it justice. So we have a lot of this fine grain organic rich sediment that accumulates in locations in the lagoon, and it's kind of like this thick, gross, really smelly mayonnaise type material. And it comes from soil runoff, decaying of organic material, things like grass clippings, which are a big one. Even just today, driving around, I'm still seeing people blowing their grass and yard waste into the street, which eventually finds its way to the lagoon. And some of the issues with this muck is that it is so fine grained, it can be easily suspended, especially in such a shallow system like the lagoon. And one thing that we're finding, and Dr. Fox has been really hallmark in this, is that the muck can also harbor nutrients, which can then leach out into the water column and cause algal blooms or exacerbate algal blooms. And so, unfortunately, we've also had our share of algal blooms in the past decade. The 2011 one, that was a very big one. We had this kind of primary site in the Northern Lagoon with this secondary site. But one of the consequences to the super bloom was this decline in seagrass, and this quite drastic decline in seagrass as a result of this super bloom. We also had our 2016 brown tide, again, more in the northern lagoon, where we had increased algal or phytoplankton growth. And what was scary about this one is that we had this significant decline in dissolved oxygen associated with the bloom. And if you were around the area at the time, or maybe you weren't even around the area, but this had worldwide recognition, we just had these massive, disheartening fish kills that were seen for miles in our lagoon. And more recently, we had one in the fall, which was a cyanobacteria, a blue-green algal bloom. So turn the water now a pea soup color, and also associated with dead organisms as well. So we've had muck, we have overfishing, we have algal bloom problems. Where do we go from here, right? So we want to kind of turn this doom and gloom into a positive story. What can we do? And so if we think about working towards a solution, we can look at it as 5 R's. So remove the muck, which we know harbors a lot of nutrients and possibly other harmful things. We can work to reduce the amount of nutrients and particulate matter that are entering our water system. We can rebuild infrastructure. We can restore our ecology and work on restoration. And then, of course, we can research so we can learn more and be more efficient in the future. And what we're going to talk about is this R, this more restore, where Dr. Fox and I are at the moment with regards to our research. And with that, I will turn it over to you, Dr. Fox, and do my best to advance your slides in a timely fashion.
Well, thank you, Kelly, and thank you, Jillian, for the wonderful introductions. So as Kelly talked about, the restoration of the Indian Lagoon, before we start, we really need to know what the problems are that we're dealing with. And one of those has been the accumulation of this muck that Kelly talked about. And so one of the things that FIT has been very involved in is identifying the locations and the quantity of this muck throughout the lagoon. And so what you're looking at here is just some contour maps of the distribution of this material. And current estimates indicate that this muck probably covers somewhere between about 5 and 10% of the lagoon bottom. And so we keep that in mind as we look at some of these other restoration techniques. You can go to the next slide. And so the accumulation of this muck, as well as just degraded water quality, has led to just this not necessarily pretty environment. And so if any of you, I would ask the question, if you can raise your hands, how many of you have had a chance to stick your head underwater in the IRL? But because many of you have not had that opportunity, I'm going to take you there, or we're going to take you there. So that we're sticking our head underwater right now. And we can go our next slide. And we've just entered the Florida Keys. So this is just to give you some contrast to our next slide, which is the Indian River Lagoon. And if you really like the color green, you'll like diving in or putting your head underwater in the IRL. And this is actual footage, right? And so you just saw me put my hand into one of these muck deposits. And I did that to show you some contrast, right? If you hadn't seen my hand there, you might not know you're actually looking at the bottom because it's so monochromatic, right? It's virtually devoid of life. It's just this lifeless pit that's accumulated on the bottom of the lagoon. And so just keep this in mind as we're talking throughout the rest of this lecture. So we can go on to the next slide. And so what is this stuff, right? Kelly did a really great job introducing it. But this stuff, it's been, if you have a chance to feel it, it has kind of the texture of black mayonnaise. It smells like rotten eggs. And you can think of it as kind of fine-grained organic rich sediment, right? So muck is kind of a local term for it. This is just fine, so little tiny particles that have a lot of organic matter associated with it. You can kind of think of this as almost like a compost, right? But think of it not as a compost that you're using to grow the beneficial things. Think about it as compost that's helping to grow the weedy species, some of these algae. And so what does compost do, right? It's a source of nutrients, a source of nitrogen and phosphorus. And so that's exactly what we're seeing here. So this stuff contributes, as it decomposes, is contributing roughly 30% of the total annual loading of nitrogen and phosphorus that are coming into this system on an annual basis. And so dealing with this stuff is really important as we think about restoration of the Indian River Lagoon. And so from this discussion of muck, I'm going to talk today about two of the projects I'm working on, two of the many projects, but I focused on these two because they kind of were spurred by a major public interest in restoration of the lagoon. And the public we have many ideas coming to us. And two of the things that I hear over and over again are, let's put in another inlet, right? And so what if we enhance the circulation in the Indian River Lagoon? Would that help improve water quality? So I'll talk briefly about that project. And then I will talk about another project that came from public interest in using aeration. So can we add bubbles to the lagoon to help decompose away some of this muck and help some biogeochemical processes to minimize the negative impacts of all of those nutrients? And so those are the two projects that I will talk about today. So the first one, talking about opening a new inlet. Inlets are fantastic, right? If you have a chance to get to Sebastian Inlet or maybe to Blue Heron Bridge, where there's some really beautiful diving and snorkeling, those are both very near inlets. And so at high tide, we have water coming in. So I have a little animation here. High tide, ocean water comes in, it mixes with the lagoon water. And then at low tide, we have kind of this combination of ocean water mixed with lagoon water leaving. This impacts a relatively small area, right? You go to Sebastian Inlet, the water's very clear, but you go a kilometer north or south and the water quality degrades pretty quickly. And so how can we use this methodology to improve water quality throughout a larger area of the lagoon? And so to do this, Florida Tech, a lot of different investigators have gotten involved in what we're calling the Restore Lagoon Inflow Project, where we're investigating whether or not creating circulation in the lagoon would be beneficial. And then we can make recommendations whether or not this is something that should be considered. And so inflow would create circulation throughout the lagoon by creating a one-way inflow at one location. And then the water that comes in has to go out somewhere, so it would go out through some of these existing inlets. We can do this either using natural tidal cycles with something like a weir. So at high tide, water comes in, but the water has to go out somewhere else. Or we can have pumps that can be turned on and off to kind of achieve some of the beneficial environmental impacts. And this could be in the wintertime, hypothetically creating warm water refuges for manatees. We could use this system for a lot of hypothetical positives, but we have to be careful that we're not going to damage the ecosystems that do exist there. And so that's the purpose of this study. And so I've added this not very scientific term, but as the water flows through the lagoon, we're seeing some really cool geochemistry, right? We're seeing some really cool biogeochemical processes that can help reduce the impacts of nutrients in the lagoon. And it's not just flushing them out, right? We're creating a process that actually helps to improve the water that's already there. And so how on earth do we study this, right? And so we collect cores. And so on the right, you're seeing a picture of a sediment core, and you see one of our divers in the background. So these are collected by divers, or we can wade in from the shore. And we do some in situ work. So we look at these, we monitor them in place, but we also, to do some experiments, bring them back to the laboratory, and we put them in this contraption that's sketched on the left. The sketch is because you can't really see what's going on when I show you the real photograph. But we're able to take these sediments and change the water that's on top of it, right? We can put ocean water on it. We can put a mixture of ocean water and lagoon water, and we can look at how the nutrient cycling changes as we perform these experiments. And so big picture, small changes to the temperature and salinity and DO that would happen from exchanges of lagoon and seawater can have large impacts on this nutrient cycling. So the number one thing that we're looking at is during summer months, the seawater tends to be a degree or two cooler than water in the lagoon. And so decreasing the lagoon temperature would actually have a significant impact on reducing the inputs of nutrients from this muck. So it would reduce that decomposition, bacteria are a little bit less active when it's cooler, and so they're not going to decompose that muck or that compost as quickly. And so this could lead to significantly less nutrients entering the system from this muck. Also, as you bring in that slightly saltier seawater, you're going to increase, and this is a little bit of technical term, you're going to increase the molecular viscosity of the water. And another way to say this is salt water is a little tiny bit thicker than fresh water. And on a molecular level, this slows things down a little bit. The rates of diffusion are actually a little bit slower. And so we're having additionally lower fluxes as a result of the slightly higher salinity. Finally, and so we'll show this here, is as you increase and stabilize the dissolved oxygen concentrations. And so what Kelly was showing those, or Dr. Hunsucker was showing those DO values crashed during the fish kills. If we can stabilize those values by using something like ocean inflow, we can significantly decrease the internal loading of nitrogen and phosphorus. And so on this next slide, if you look at the blue line, that's virtually continuous monitoring of dissolved oxygen shown on the right axis there. And 6 to 8 milligrams per liter is roughly where we should see it, right? But you can see that in December of this last year, there was actually a brief fish kill. You may or may not have heard about it. And fortunately, we were out sampling at just the right time to capture the impacts on the geochemistry of this event. And so oxic water and healthy sediments can actually sequester phosphorus. And so phosphorus in the water is actually going from the water into the sediments. It's being removed from the water column in a healthy system. But when we have these oxygen events, right, the sediments actually can dump a lot of phosphorus back into the water, and they can actually act as a major source of nutrients to the overlying water. And so stabilizing the oxygen is really important. And so inflow of ocean water can actually help to circulate this water and prevent some regions from going anoxic. And so this graph here, you're looking at dissolved oxygen concentrations in water over some of those muck deposits. And so the blue line is showing the DO over muck deposits, and very frequently it's going anoxic. This would kill fish, right? The fish just choose not to live there. There are no crabs living there. There's no benthic fauna living in these regions. And so if we can circulate the lagoon a little bit better, we can make this blue line maybe look a little bit more like that green line that's kind of a healthier system. And so all of that is showing that circulation in the lagoon has many benefits beyond just flushing. And so we're looking at the good and the bad and whether or not this is a viable component to a multifaceted approach to lagoon restoration. And so talking about DO, I'll jump into the other project. And so this spurred, again, from intense public interest in using something like aeration to improve water quality. And it was pretty successful, right? It didn't do much to decompose muck, but the water quality improved just a little bit. And so we asked the question, can we improve upon the results that came from this aeration study and enter the repurposed bottle caps? And so when I talk about oxygen and its impact on reducing nutrients, there's these big fancy chemical terms, nitrification, denitrification, anammox. And these are all just describing how bacteria can take the nitrogen that leads to algal growth and remove it from the system. And so wastewater treatment facilities, aquaculture, so fish farms, large marine aquaria use technology like this to get rid of nitrogen. And they use various what we call media. And all this media is doing is providing the things that the bacteria need to be able to do these reactions. If you look at the third beaker from the right, that's lagoon sand, right? So we're looking at, is there a way that we can supplement and give these bacteria a place to live because their natural environment, the sand in the lagoon, has been degraded over time. And so if you notice on the right, you see a plastic bioball. You may have seen these in your fish tank or your friend's fish tank, and these actually worked pretty well in the system that we're developing. And so we were joking around, right? We don't want to buy new plastic. And we ended up, after some experimenting, saying there's got to be something already out there. And so we ended up trying a couple different plastics, and through some trial and error, we ended up at plastic bottle caps. And so I can explain the advantages of this after the talk if you'd like to hear more. So we can go on to the next slide. And so why bottle caps, right? There are commercially available products. Bottle caps are made out of high density polyethylene and polypropylene, which is the same materials that these commercially available products are made from. So the bottle caps, they're also BPA, they're food grade plastics, right? They're not containing a lot of the really harmful chemicals that other plastics are composed of, and they're readily available globally. So we're thinking beyond the lagoon, right? Can we build a system inexpensively using things that are found? If you go to rural and underrepresented communities, you will find a surplus of bottle caps. So we're providing a responsible way to dispose of these bottle caps in a system that will help to improve water quality, hypothetically, anywhere on Earth. And so this is a real advantage over increasing plastic pollution by manufacturing new plastic materials. Finally, how do these compare in terms of efficacy? We have 4/5 of the surface area on our bottle caps as we would on this commercially available product. So we're getting at least 80% of the performance out of this material that is a lot cheaper. It's not producing any new plastics, and it's available globally. You can go on to the next slide. And so to set this up, this is our laboratory system. We started out in the lab. We set up a system where you can show my little arrows here. We pump lagoon water in to this first tank. We're controlling, you see the gas cylinder there, you see some pumps and some control valves. We're able to manipulate the oxic conditions. We're able to manipulate what other things are going into the system. And we can promote the nitrification in one chamber, and we can promote the denitrification in the other chamber. And together, these processes help to remove nitrogen from the system. And so does it work? So we look at this graph of the laboratory results. And if we compare the inflow, right? So the inflow is just the basis. And then we look at the percent decrease. We're seeing greater than 95% removal after just 8 hours. And so this is fantastic. Right, so we've been experimenting now, how short can we go? Because the shorter we can get these residence times, the more water we're able to treat. So I keep going through this because I don't want to run over time. So the big question is, can we take this little fish tank experiment and scale it to something that's actually going to help the lagoon? And the answer is yes. Right, so what you're looking at here, it's pretty ugly. This is our field system. And so I want to clarify two things. The bottle caps are not just going in the lagoon. They're going in bags in a contained treatment system. And so you actually can't see them in this picture because they're contained underneath a ultraviolet barrier. And so one of the questions that we get, right, people say, don't put plastics in the environment. They're going to break down into microplastics. And so we're well aware of this, and we're actually now studying it. And so there are two things that lead to the production of microplastics, right? So the breakdown of larger plastics into little microplastics is the result of ultraviolet radiation. So the sunlight breaks down plastics, and then physical forcing of plastics breaking against the rocks can break into smaller pieces. Both of those have been accounted for. There's very low energy and no sunlight getting into the system. But to make sure we weren't doing any harm, we've started analyzing this. And so the next photos of Abby Gearing, one of my graduate students, has really been critical in making this project feasible. And I owe her a lot of credit for helping with these slides. And so on the next slide, you can see that we were blown away, right, at just the microplastics that we're seeing. There is 1/3 as many microplastics leaving our system as entering the system. So we were not expecting this at all. We started out just to make sure we weren't doing anything bad. And in fact, we are helping to remove microplastics from the water. And so if you look at the microplastics there, they're all kind of fibrous. And that's largely because most of the microplastics out there are coming off things like our clothing, right? If you're wearing synthetic clothing, when you wash that, your lint trap is now full of microplastics. Not all of it is caught. A lot of it's being blown into the air that washes down tributaries into the lagoon and ends up in the lagoon sediments. And so we have very high counts coming in because we're using creek water and water that's been mixed with mud. But really cool, we unexpectedly are removing microplastics. Next slide. And so does this bigger system work? And you can see that the results are very similar, right? We are able to scale this up. And so we're now in the process of collecting more caps. We're working with schools and working with the community to educate the community about the plastics crisis. We're educating about reduce your consumption, right? Repurpose things when possible. And that's all leading to these really fantastic results. Another unexpected result Again, we went into this with the goal of reducing nitrogen in treated water. Something else we just happened to notice is the water was clear coming out the other side. So this is just a picture from one day. You can come and I can show you this any day, but we see clear water coming out of the system each time. And so one of the ways that we can quantify water clarity is using a term called turbidity. And so we measure turbidity. And so you're seeing here untreated and treated water. And the turbidity in this weird turbidimetric units is 15.5 in the untreated water and 5.8 plus or minus 4.1 in the treated water. So again, 1/3 as much turbidity coming out. We're seeing clearer water, fewer nutrients, fewer microplastics leaving this system. And so another potential, so we've identified a lab to help us with this. A lot of people that come and yell at us about plastics or give me a hard time about plastics, they say, why are they bad? And they're bad because they sorb organic pollutants. Organisms ingest those plastics, their gut contents leach those organics into the organism, and they're exposed to high concentrations of some of these toxins. But can we use that in a contained system as a benefit? Can we sorb those toxins onto the plastic within our contained system and then help to remove those contaminants from the water? So there's some very recent literature from 2020 showing that this is possible, using plastic in wastewater to actually remove organic pollutants. And so we've identified a lab at Florida Tech that's going to help us, I believe, to investigate that potential added benefit to this system. So I'm just about out of time, but I'll finish up with a big thank you. So one of the greatest things about this is it's allowed us to get outreach. We're in the community. We're giving virtual lectures. We're giving talks. We're providing information about reducing your impact on the environment, repurposing things when possible. And if all else fails, then recycle. Recycling is not the solution. It is a band-aid. The reducing and repurposing are absolutely the best things we can do. And so this is just a list of the local schools that are helping. We have people from Canada, from Arizona, Colorado, New Mexico, New Jersey, Vermont. I can't list them all, who have reached out to us in support of this. And the last comment I'll make is some of the people who come in as skeptics, they see the data that we're able to show them and they leave as supporters. So I really appreciate this opportunity. I'm out of time, so I'm going to hand it back to Kelly. Thank you.
Yeah, thanks. Sorry, my internet cut out for a little bit, but I hopefully didn't interrupt you or get you too off track. So I'm gonna take it over, and my research is a little bit different than Dr. Fox's. So I'm more on the ecology side of things, and I'm going to talk about two specific projects that we have going on, looking at oyster and overall just ecological restoration efforts. And the first is our Living Dock program, which we started in 2013. So similar to how they do oyster restoration efforts in the northern portion of the lagoon and really in coastal ecosystems around the country and worldwide, we utilize these oyster mats. And so this is an aquaculture grade plastic. We attach these dead and dried oyster shells to them. And instead of putting them on the lagoon bottom, what we do is we wrap them around dock pilings. And our approach to doing that is because we are then suspending the oyster mats up. We're elevating them off the lagoon bottom so we don't have to compete with things like muck, which we know nothing wants to live in because it's so anoxic. We also don't need any special permitting because we're not putting anything on the lagoon bottom. We're using an existing infrastructure. And what we're doing is we're creating almost increasing the surface area and changing the surface area of the dock. So instead of now a dock piling that has pressure treated wood, which you get very little growth on, we're using these natural substrates of the oyster shells. And the oyster shells are known to have special chemical cues that attract oyster larvae that's present in the water column to come and settle on the shells. But our approach, and the way I like to think about it, is it's not a weed if you don't want it. And that's kind of the approach that we use in our lawn, and it drives my father crazy, but the same approach can be applied here. Yeah, we would love to get oysters growing on our oyster mats, but there's so many other things out there that also filter the water. Some things that we don't really know about, things like sea squirts and barnacles and sponges, and they all can help increase water filtration. So our ultimate goal in doing this is to increase water filtration and give a surface area for these natural organisms so they can help improve water quality. And so this is a big community project. It's mostly driven by community involvement, whether it's a Boy Scout or Girl Scout troop, local neighborhoods, local organizations. We work really heavily with the community. They build all of the oyster mats. The staff and students at Florida Tech are the ones that typically deploy them along docks. I've already mentioned this a little bit, but some of the benefits of wrapping the pilings is so that they don't get buried in the muck. It's a pretty easy process, and we can pretty much deploy it anywhere as long as the conditions are pretty good. Obviously, we have to make sure that the water depth is sufficient so that the oyster mats aren't sticking out of the water for significant periods of time. Some immersion above water or exposure above water is fine. These things can handle a little bit of drying out, but mostly we want to make sure that they're immersed. And so, as I mentioned, we've just partnered with many community groups since 2013. We have a number of students who do associated science fair projects with the oyster mats that we deploy. This is Rosie. This was a couple years ago. She actually won first place in our science fair project. And we have over a dozen docks, I think, by now, everywhere. We've mostly in Brevard County, so Cape Canaveral area down, and we have one in Sebastian, and we're talking about doing one in Fort Pierce. In 3 weeks, we'll have a deployment at the Manatee Center in Fort Pierce, and then we're going to do one in Vero Beach. Due to COVID, we're quite backlogged with our efforts and getting out there to assess docks and work with the community just out of some safety protocols, but we have quite a huge interest from the community, and if you're interested in learning about this, I can definitely talk in more detail after or at another time. So you're probably wondering, well, what's the efficacy of doing all this? And so I mentioned that oysters were the big one, and oysters we know have been over-harvested from the lagoon. And one of the great things about oysters, in addition to being tasty, I love to eat oysters, is that they filter a significant amount of water. And they can filter, a healthy adult oyster can filter up to 50 gallons of water per day. So that's a pretty significant amount of water that they can pull in. And when they pull in the water, they can retain a lot of the suspended particulates, whether it's algae or abiotic or kind of other suspended particles. And then we push the water back out, it comes out cleaner. And as I mentioned, our project, it wants to promote the growth of a lot of organisms, not just oysters. So things like barnacles and sponges and mussels. And my favorite are these sea squirts. They look really gross, but they can actually filter 24 gallons of water per day, which is a pretty significant amount. And they can filter particles smaller than the oyster. And these guys are prevalent all throughout the lagoon, because who's going to want to harvest them to eat them, right? So we really should be trying to promote the growth of some of these other organisms too. And that's what we do. So here's an example of some of the oyster shells that we had put in and what they actually look like. So I like to joke that the stuff doesn't photograph well. It doesn't look very pretty, especially if you have an untrained eye. But in actuality, it is quite impressive. So this is what they would look like. There's a ton of different things growing on them. Right here, these little blobs, these are those sea squirts that I just mentioned that can filter a lot of water. So I wanted to kind of get a sense, do like a little lunchtime experiment and see what the benefit of these oyster mats could be. So we set up this experiment, just like I said, lunchtime. So it was kind of over the course of a few hours. And we set up 2 tanks, one with lagoon water with these oyster shells that you just saw on the last slide, and one with lagoon water with no oyster shells. And we took a photograph, I think it was every 15 minutes over the course of 4 hours. And if it doesn't want to play. That's weird. I promise you we tested it out beforehand and it doesn't want to play. Huh. Okay, well, that's a bummer. I apologize for that. It did work earlier. And now I think my and now I think the presentation froze. Let me just stop sharing. We have too large of a file, Austin.
Yeah, maybe try like Xing out and then launching it again.
Yeah, it won't let me stop share for some reason. I don't know if either of you can.
I'll try. Hold on. All right, you can try to reset.
Okay. Yeah, I don't know. Huh. Maybe it's my mouse. Austin, are you able to share the presentation? Maybe you'll have better luck than me.
Yeah, let me.
Okay, actually, Austin, let me try again. I think I figured out what my problem was. So let me just try again. I apologize. Usually my stuff's pretty good, but technology sometimes. So here's the video. And so you're going to see the two tanks. On the right has the shells that have the organisms. On the left, the tank without any organisms. And of course, we put a charismatic manatee picture behind so you can see the improved water clarity over time. And those kind of weird snot ball-like things, those are the sea squirts that I said were so good at filtering out the water. So we're almost at 4 hours now. And you can see improved water clarity on the right versus on the left. So obviously this was not a super scientific controlled experiment. So you're getting some settling out, but you can see the difference in the tanks. So that was really promising to us. So what we did after that is we did a more scientific approach where we harvested these oyster shells covered with the growth from 4 different locations throughout the lagoon. And we actually looked at how they filtered out the chlorophyll A, which would be representative of algal species in the lagoon. And we did it over the course of a 48-hour experiment. So what you're seeing is just some preliminary results. So this decrease from so when we dosed the tanks with algae over 48 hours, and how you see this decrease at our sites. And what we're going to work to do is look at this decrease over time and relate it to what's actually growing on the oyster shells. And I will just quickly, I want to mention another project that we have. So within the oyster restoration field, there had been this, a lot of use of this aquaculture grade plastic. And these plastic mats stay in the lagoon or the estuary for a very long time. So there's been this big push recently to look at non-plastic alternatives. And our approach to this was doing a concept called mineral accretion. So instead of using plastic mats, we use these steel mats that we hook up via wiring to solar panels. And kind of sounds like a crazy idea, but it's actually widely used in coral reef restoration and was first kind of studied extensively in the 1970s by Garreau and Hilbrits. And they use it quite widely in coral reef restoration. So they cathodically protect the steel, and they allow for this calcareous chalk to form on the steel substrates. And in doing so, I'll explain kind of the chemistry around it here in a second. There's all these added electrons around the steel that is actually benefit for the calcium carbonate loving organisms like coral reefs. So what is mineral accretion and how does it work? So instead of using a plastic mat, we're going to use a steel mat. This acts as a cathode, and it is hooked up to a solar panel, and these white lines denote those the wiring that you had seen a couple slides ago. And we have some kind of inert sacrificial anode. It could be something like magnesium or mixed metal oxide. And it's inert and it's sacrificial. And that is important because that means that electrons want to flow from this anode through the wiring to protect our steel mesh, because we're trying to prevent it from corroding. So these electrons come to the surface of the steel mesh, and in doing so, it actually increases the pH. And by doing that, it kind of sets in motion a series of chemical reactions. And basically what that means is that it causes certain ions that are always present in seawater, calcium and magnesium, to precipitate out as calcium carbonate and magnesium carbonate, limestone, or what you would normally see for coral reefs. And so what they had found in the 70s is that these conditions actually promote the growth of organisms that need calcium carbonate, and in our case, oysters. And so we did a study where we compared these steel mats to plastic mats. We had little sacrificial coupons so we could look at how this accumulation of the calcium carbonate changed over time. Here's an example again of the setup. So we had these steel mats. Here's our wiring, and then our solar panel. You can't see my anode in the picture, but it's there. And we put them at 3 different sites in the lagoon. We had one up in Port Canaveral and then 2 down in kind of southern Brevard County. And I mentioned the salinity and temperature. The salinity is the big one. There's a significant difference, especially between Port Canaveral and the bottom 2 with regards to their salinity. And that's important for this mineral accretion and getting this nice chalking to form. And this is what the chalking thickness looks like on those steel mats. And so we want this chalking to form. It means that the mineral accretion is working and that we're having these enhanced electrons available for our oysters. And these are those 3 sites. So our Port Canaveral, our Melbourne Beach, and our Grant. And if you look at the pre-chalking that we did before we put it in the water, and then at 1 month, 2 month, and 3 month, you see this nice increase regardless of the site. And what's impressive is, or important, is that up in Port Canaveral, where we have a higher salinity environment, we had a greater thickness. And so the higher the salinity, the more ions are present, means that the more chalking we can get. But we still had a good amount of chalking at both our other 2 sites. And then this is the last thing I want to mention. We also looked at oyster settlement. And on the top, we have our steel mats. On the bottom, our plastic mats. And these are the oyster counts that we took every week for a 3-month period or 12 weeks at the 3 different sites. So on the top, you can see this is our Melbourne Beach site, was that middle site. At the end of the experiment, we had somewhere between, I think, 70 to 75 oysters on our mats. But if you look at the plastic in comparison, the same site kind of topped out at about 10. So a significant amount more of oysters settling on the steel than the plastic mats. So we thought that was really promising, that the steel can promote the growth at an equivalent rate or even higher than the plastic mats. And then I'll just end with this. Of course, we want to filter the water, but these mats and these the growth actually provide habitat for both attached organisms as well as mobile organisms. I realized I ran through the technology and the results pretty quickly in this, but we did just publish this in Ecological Engineering Journal. So if you're interested, and I can explain obviously in person more, but I'm also willing to share the paper as well. So both Austin and I, we talked about projects that just had a ton of assistance, ton of people working on them. So we obviously want to acknowledge everyone, both past and present, who has worked with us, as well as our many different funding sources. And hopefully, I know we went a little over, but I think we have 10 minutes or so for questions.
Yeah, that's perfect. Great presentation from both of you. Thank you so much. And I want to open it up for questions. So if anyone would like to go ahead and enter them in the chat box, or if you want to unmute yourself, I will allow you to unmute if you want to ask in person. I did see a couple. Al asked, what about erosion or corrosion of the steel mats, or are they stainless or aluminum?
Kelly, you're
I muted myself in case I had background noise. You never know when my four-legged office mate wants to talk. Yes, they're not aluminum. They are stainless and they're ungalvanized. So we select a specific type of material, and then the cathodically protecting it would mean it wouldn't corrode. So we're trying to get that nice chalking to develop. And something I didn't mention, what we did before we put it in was we did this pre-chalking to kind of get this nice calcium carbonate layer on the surface before we deployed it at each of those 3 locations.
All right. Douglas Ludgren
Yes.
has a question. Go ahead.
Hi. This muck thing really gets my attention. I was vacationing for a weekend in the Pocono Mountains of Pennsylvania about 10 years ago. There was a similar muck configuration that messed up an entire lake. Obviously, recreational boating was gone, no more swimming. And I noticed that there was a ring of houses around the lake, and presumably they all had septic tanks, but exactly the same sort of muck you're talking about. I guess that's a comment for Kelly.
okay.
Oh, I'm sorry about the muck around the septic tanks.
No, I just saw similar muck in a lake in Pennsylvania in the Pocono Mountains, and it was surrounded by residential houses, which presumably had the same sort of nutrient inflow from septic tanks. And I'm just wondering, is this found in other places in the world besides Indian River? I suppose it is.
Oh, yes. Sorry. Yes, definitely. What you're saying, because the causes could be the same with the decomposing organic matter. And especially if you're a residential and you think about all the grass clippings and yard waste that can blow in there. And then we have colleagues over in California. They don't call it muck. They call it something else. And I can't quite remember what they call it. But yes.
And just to add to that, so this is a global issue, right? So eutrophication, which is just too many nutrients, whether entering from, I see, septic systems or stormwater runoff or anything. This happens in freshwater, it happens in seawater. The muck or the fine-grained organic rich sediments, right, that we're locally calling muck, behaves a little bit differently in seawater than it does in freshwater. And we're kind of blown away. So one of the reasons for investigating aeration was it's been very successful in freshwater lakes. And so you often see, if you drive around, you'll see freshwater lakes with bubbles coming up the middle. And it's incredibly effective at improving water quality in lakes. And so that's one of the reasons that the public was so interested in aeration. It's very different response in the brackish environment. So we're having to use some slightly different approaches. But yes, it's the same kind of materials, just behaves differently depending on where you are on Earth.
Thank you. Real quick, just a quick follow-up. Kayaking a few months ago in like December at the Pineda Landing, where there's a beach area on the western side of the river. That water for about 2 weeks was almost like the Bahamas. And I thought it was very strange, but it was wonderful. I sure would love to see it again. So that's all. Thank you.
Well, so that's actually a fantastic comment, right? So about this time of year, the water quality in the lagoon improves. And that's just because there's been a drought. We are making progress. There are projects happening to fix some of the problems in the lagoon, but you can't be misled by just the seasonal changes in water quality. So we're hoping to improve long-term water quality and just conditions in the lagoon. But you are, every year after drought, you're going to see clear water. Once it starts to rain, we see the summer rains, that starts to bring in new stormwater. It starts to bring in new groundwater that contains some of this septic material. It contains some of the material from fertilizer. And so those things are all going to lead to, during the summer, you'll notice, and I think you've probably already seen, the water quality is starting to decline again. And that's this just sort of seasonal cycle of changes to water quality.
Thank you.
So there are a ton of questions popping up in the chat, and I don't know if we're going to be able to get to them all, but I can send them to you guys after the event if you have time to answer them. We run out of time. I wanted to ask you both, what are some things that we can all do to help in our everyday lives? And you know, I've gotten a lot of questions about volunteering opportunities. It seems like everyone is really interested in what they as individuals can do to contribute when they can.
Yeah, I can't speak for Austin, but I definitely, if anyone wants to reach out and learn about some of the volunteering efforts with our oyster mat projects, I think hopefully in the fall, once things calm down with COVID, we'll definitely have more community events where people can come out and help make oyster mats and install them around dock pilings. I know with Austin and his bottle cap program, I was watching my neighbor's dog and I saw that they were collecting the bottle caps, which I presume are gonna go to Austin. As far as everyday things that people can do, I mean, just being aware of what you're doing, what you're putting on your lawn. Do you need to fertilize? Are you fertilizing during the correct season? Are you blowing your grass clippings into the street and your yard waste? Because they're going to make their way to the lagoon and contribute to muck. So those are just some kind of really simple things that people could do. Austin, I don't know if you want to add anything.
So I think this is really cool. I've just recently got into this outreach component of it because I've been kind of locked away in the science, thinking about all of the technical details. But a few of the things that we've learned is, and so towards the nutrients things, fertilizing. You go to Home Depot or Lowe's and you buy a bag of fertilizer, and I think the rate of application is 1 bag, right? That's way too much. And so even the recommended amount of fertilizer. So I helped one of my friends, 4th graders, with their science fair project, looking at when you apply the recommended amount of fertilizer, how much actually gets incorporated into the grass versus how much just ends up in the groundwater. And even at the recommended application rate, almost 90% of it is just the first rain, it goes into the groundwater. And so fertilizing is just so nonsensical in Florida. I mean, you might have a weed-free lawn. It may be this monoculture, but that's not what we want, right? We want these diverse lawns, and we don't want grass in the first place. But if you are going to have grass, you don't necessarily need to fertilize. If you do now, try skipping a few applications. So that's a huge step that you can take to help. The bottle caps project, one of the coolest things that's led us to do is when you start to collect your caps, right? You see this pile accumulate because you take out the recycle every day or every couple of days, and so you don't see the accumulation. But when you just see this pile that represents your consumption of waste, you start to realize just how much waste we all produce. And the coolest thing that I've seen is somebody who starts to bring me fewer caps the next time, right? And so people changing their behavior. And so just recognize your impact and make choices that are better for the environment. And the last thing I'll comment there is look at the alternatives. The alternatives aren't always better. So there are a lot of alternatives that we're looking at. And when you look at the cradle to grave of those alternatives, just the cost of the environmental cost of producing some of the alternatives. And so a fantastic example is the reusable straws. That was a hot topic for a while. If you actually look into it, you have to use those reusable straws many, many, many times before the impact on the environment actually is less than the disposable straw. I'm not condoning using disposable straws, but just make sure the alternatives are actually better. So.
Well, those are great tips from both of you. Thank you so much. And I hope that everyone has taken a little piece of inspiration from this presentation, and that you can take it with you and talk to your family about it and spread the word. And I know some folks have joined the event late, so I just wanted to let everyone know that I've recorded this, and that as soon as I get the link from Zoom after the recording has been processed, I will share it with everyone. And I will also take all the unanswered questions from the chat and send them to Kelly and Austin to see if they can get those answered for you. And if you have any other questions at all, please feel free to reach out to me, and I will do what I can to help.
I guess just real quick, I know Charlie has posted in the chat, there's a talk tonight by the IRL Coalition at 6 p.m. And so you can register and learn, I think, on a more broad scale about Indian River Lagoon restoration.
Awesome.
And so I guess one last comment is I do see a lot of comments in the comments tab, so we'll try to respond to those via email. One of them was, where can they drop off caps? And another fantastic thing is we're promoting small businesses. And so we have, in Melbourne, we have the Sun Shop if as a drop-off location. We have the Tiny Turtle in Cocoa Beach. We have Brevard Zoo are some of the other drop-off locations, or you can arrange a drop-off at Florida Tech. So
Excellent.
much appreciated. Thank you all.
Thank you, everybody, for joining us today, and I hope to see you again at another Lunch and Learn lecture in the future. Have a great day, everybody.